Hi, we are the Alfred University team, and our case study was Cheyney University. And
we're just going to introduce the team here real quick. First, I'm Finn Vossler. I'm dual majoring in renewable energy engineering and mechanical engineering.
I'm Andrea McDonald. I am majoring in renewable energy engineering.
I'm Scott Kimichek, and I'm majoring in mechanical engineering.
I'm Dylan Keenan, and I'm also majoring in mechanical engineering.
I'm Justin Charmer, and I'm also majoring in mechanical engineering.
I'm Tyler Kemet, and I'm also a mechanical engineering major.
And I'm Tessa Bullo, and I'm a renewable energy engineer.
So just to run through what we plan on going over in this presentation, we are going to start with our approach to this competition, and then move on to our solar plus storage design, followed by our expected operation with the distribution system risks, our financial performance, the development plans, and then wrap up with the innovation and analysis and a conclusion.
So our approach to this project was pretty straightforward. We began by analyzing Cheyney University. We looked at its energy consumption, both like over a day, as well as like over a longer period of time, like a year. We also looked into the local distribution system, so we could have a better understanding of what power we can export from the university. We also looked into the space it has, like roofs and fields for PV panels. We looked into what their specific system resiliency requirements are, in this case, the Science Center. And then to finally build our design, we used a few different softwares. Aurora, most prominently for the PV system. And we used both Reopt and Energy Toolbase to optimize our system and work out the battery capacity.
So our team used Aurora for the PV designs. We analyzed multiple installation options for the system. Many of our locations are seen on the left side of the screen in a chart with their sizes and annual production. Our total PV size was 989.22 kilowatts with a total annual production of 544,716 kilowatt hours. And our largest installation was the ground mount at the athletic fields with a size of 410.4 kilowatts, which gave an annual production of 120,753 kilowatt hours. Then for our storage system, we use Energy Toolbase and Reopt. Reopt helped us a lot determine the resiliency, and Energy Toolbase we used to determine our financial, which we will talk about later. The energy storage system has a capacity of 1,000 kilowatt hours and a power rating of 330 kilowatts. This gave us a total ESS energy discharge of 157,300 kilowatt hours.
So our system is expected, once it's all fully operational and all set up with the construction and everything, should be operational year round. The only thing that'll affect that should be weather, things like that, things that would either clouds, stuff that would affect PV systems, or in the area where Cheyney is, snow could even be an issue. So it's possible as it's built and things like that, they may need to come up with systems to clear snow off panels, things like that. But the average generation depends on month. And normally the PV generation peaks around 12 or 1 p.m. And obviously the generation only occurs during the daylight hours. With the battery system we have set up, it should be operational for if there was a grid outage, that the Science Center would still be able to have power.
Tessa, you're
Tessa, you're muted.
Thank you. So we also analyzed the distribution system risks, and we did conclude that with the system we created, there are minimal risks. We kept it under 1 megawatt to avoid the net metering, which would just result in losses. And then roof mounted systems are connected to the buildings and they can sustain the load. And the ground mounted systems only a short way from interconnection, so the cost on that should be relatively low. And the node capacity does need to be taken into consideration, and the utility company will have to run a study on that to make sure that everything can be connected in the places we specified, because you never know, there are always unforeseen risks and everything.
So the first thing we did to run our financial analysis was using the Excel sheet given on heat spraying. And this really only takes into effect the solar system, not the storage system. And some key points to point out was that our total cost per watt for the construction was $1.50. This was based off of the US benchmark 2021 ground mount installation price point, and this gave us an aggregate project cost of $1,793,956. And our PPA price had actually ended up being a lot higher than we had anticipated, but it's hard to be competitive with what Cheyney University already pays, because they pay a pretty low price already, and that gave us a project IRR of 7.55%, which was what we were aiming for, with the NPV of $4,372. We also ran a re-opt analysis just to look at the resilience of the system to make sure that it can operate for a 24-hour outage. This is overestimation of how long the outage needs to be, but it's always better to be safe than sorry and kind of figure out worst case scenario, the longest that we would need to run our critical loads without being connected to the battery or to the grid. And then re-opt gave us a battery power of 623 kilowatts with a battery capacity of 32,621 kilowatt hours. And re-opt doesn't seem to include the cost of installation or anything like that. So with just what they pay now versus what they will be paying after their battery and solar system is installed, the life cycle savings would be around that number there on the screen. And finally, we also used Energy Toolbase to perform a separate financial analysis, and we created a new, we put in all the information that the university currently pays to size our new system for the battery storage part of the solar system. And this gave us a net PV system cost of $2,582,633 with the net storage cost of $814,000. And you can see on the screen that the annual usage for the solar power and the electric bill cost savings are all calculated from Energy Toolbase. So we were able to calculate a lot of savings analysis from that tool as well.
So here we have our Gantt chart for our development plan. As you can see, we expected the development to be finished within 12 to 15 months. To break down the Gantt chart, site control will hopefully be done in about a month. Defining the process and getting federal, state, county, and city codes situated will take about 2 months. Situating the power offtake negotiations will take about 3 months. Financing the costs and benefits will take about 4 months or 4 months each. Connecting to the existing grids and or connecting the existing grid will take about 4 months. Developing the final design will take about a month, and hopefully construction can be limited to only 4 months, although we know that construction usually gets held back due to a few risks. And these risks are financial risk, which is the case if we run out of funding for this type of project. Market risks are just a shortage of labor. Regulation risks, or if there is a late design change that needs to be situated. Technology risks are if the generation is lower than expected, or if the weather conditions aren't as optimal as we planned for. And construction risks are basically just if the materials needed to build this PV system will take longer to arrive than expected.
So this is just a look at the innovation and analysis in our project, and just methods which were gone over in the previous slides. But Aurora Solar, as stated before, was a huge part in our project, as it was what provided us the initial simulations for the PV system and gave us the outputs of energy. A minute or two ago, going over the financial analysis, which was also provided by HeatSpring, which is the next one on this list. And finally, REOP system analysis conducted, and the financial analysis of the systems, as Andy touched on as well. So through Aurora, we decided to use the Aurora inverters, as that was what was recommended by our professor. As you can see there, it has a power of 40 kilowatts per string, a maximum power of 200 kilowatts per string. And each inverter has to have the same amount of panels strung to it. And the solar panels used to convert were the Aurora sample solar panel, and same reasoning as the inverters, it was what was recommended to us. And those had a 10 kilowatt power output. Along with the batteries we chose, it had a power rating of 587 kilowatts, a capacity of 32,834 kilowatt hours, and using that provided 66,568 in energy savings per year to withstand a 24-hour outage, which is ideal for a PV system. And the design for our system is we just place them on the building or on the athletic fields. So yeah, by selecting or through our project, Cheyney University can turn to a more renewable and sustainable energy plan for their future, which will generate savings as explained earlier.